Happy New Year! It's not New Year's for you, but it's New Year's for me. It's January, what's it? The
4th.
4th. Okay, so do now. A ball bearing with a mass of 0.067 kilograms is rolling at 2 meters per second in the positive direction. How much momentum does it have? And then B, how much impulse will bring it to a stop?
All right.
Okay, well, what's that equation for momentum?
This is really, really simple, I think.
E equals mass times velocity, right?
Yeah.
Okay, and our mass is 0.067 kilograms, and we're going to multiply it by positive 2 meters per second, and our momentum is going to be, get rid of that. We just multiply them, right?
That's all.
0.067 times 2, and I get 0.134.
134. Okay.
0.134 kilograms meters per second. Those are my units for momentum. Okay, so that was part A. And B says, how much impulse will bring it to a stop?
Now, what does impulse do?
Okay. Well, impulse changes momentum,
Yeah.
right? And if it's going to stop at 0,
It's going to be the final minus the original.
it'll be the final minus initial, so that will be the final stop, right?
It's 0.
Kilogram meters per second minus that up there, right? Because this is
Yep.
the initial impulse. I'm sorry, momentum it's going.
Right.
0.134 kilograms meters per second, and that's going to equal the impulse. So what we have here is negative 0.134 kilograms meters per second, and that makes sense because what this negative sign just tells us the direction.
That's right.
Right. So the exact same momentum, but just in the opposite direction.
That's simple.
Okay. Do now another one. Woohoo! Okay. A 0.067 kilogram ball bearing going 2 meters per second collides with an identical ball at rest. The first ball stops. How fast does the second ball go?
This is conservation momentum. We need that pyramid thing.
And actually, right here, so you think?
Uh,
Right here?
yeah, you know, you could erase that
I can
right
erase
there.
this one. Yeah, these ones are. This one we're done with. Hopefully,
done
you
with
have that written down.
Yeah.
Okay. All right, so we have a
Momentum before is
momentum
equal
before.
equal momentum prime.
Okay, they're the same size? Identical
Well,
ball.
Yeah.
Or do you want to draw a picture or no?
Well, you got to do the pyramid first.
Let's do the pyramid.
I mean, a picture is good, but
Yeah. Okay, so we know that the momentum before is equal to the momentum after,
yep.
right? And well, the momentum before
We get-
involves two things. It involves that the two balls, right?
Yeah.
And one of them is moving and one of them isn't.
Yeah.
So the one that's moving is going to be, we'll just say mass. Should we say mass 1?
No, you don't want to go to the masses yet. You want to go to the P of the first one plus the
Oh,
P.
yeah. Forgot to break it down.
That's right.
Okay. The mass of the the momentum of the first one plus the momentum of the second one is going to equal, and
Same thing except afterwards.
yeah, same thing except after. Momentum second one plus the momentum of the second one after.
There you
Boom. Okay, so what's going on here? In the beginning,
Well, that first one's at rest.
so this
The second one
the
is
second
at rest.
one's
I
at
beg your
rest,
pardon.
so we're gonna get rid of this one.
That's 0.
And then at the very end, the first ball stops, right?
So that one's 0.
So this one is 0, okay? So that means we've got P1 equals P2 prime.
Now you can do the
Now,
MVs.
now we've got the M and V's. Okay, so the mass of ball 1 plus the velocity of ball 1 is going to equal the mass of ball 2 plus the velocity of ball 2 afterwards. Okay, so can we, what are we trying to find here?
Well, we want to find how fast the second ball goes, but there's something that makes this much easier. What is it? What is it about the two balls?
They have the same mass, don't they?
Ah, yeah. So if they're the same on
Oh.
both sides, what can you do?
You can cancel them.
We can cancel them.
Okay, I mean, you could just divide by the same number, but it's gonna get the same answer. But, just cancel them, okay? So we're trying to figure out this. That means that the velocity of the ball at the second ball at the end is gonna be the exact same as the velocity of the first ball at the beginning, right?
Simple, isn't it?
So what was the, so 2, right?
2 meters per second.
Okay, so that's gonna be the velocity of the second ball after.
Yep.
Sweet, okay? Which which makes sense, right? Momentum is conserved. If the first ball is going 2 meters per second in the beginning, another one isn't moving. At the end, the second one's not moving. All of that momentum is going to be transferred to that second ball.
That's right.
Conservation of momentum. Collisions. Momentum is the same before and after.
We're just restating it. Yeah.
Yeah. Okay. Elastic collisions. Kinetic energy is the same before and after.
This is a definition.
This is a definition. So if we have an elastic collision, that means our kinetic energy is the same before and after. Is this an elastic collision?
How do you find kinetic energy?
We want to know, is the kinetic energy the same before and after? What is kinetic energy? It is 1/2 mv squared.
Yeah.
Okay, so we can say 1/2. What was our mass here?
0.067 kilograms.
0.067 kilograms times our velocity, which was
2 meters per
2
second
meters
squared.
per second squared. So let's go ahead and get this answer. So we've got 0.5 times 0.067 times 2, don't forget to square it, and I get 0.134.
0.134
Yeah.
joules.
Joules. 0.134 joules. Okay.
Well, now, do we have to do this again because the
No.
balls are identical and they're going at the same velocity before and after? So
Exactly. So we just calculated the velocity of the kinetic energy of the ball before.
yeah,
Now, since they're going the same speed, we're gonna get the same, and they have the same mass.
yeah. I don't think we need to do it
We
again.
don't have to. The kinetic energy of the ball before is 0.134 joules. The kinetic energy of the ball after is 0.134 joules. Is this elastic collision based on this
Yes.
statement? Absolutely. Yes. Okay. So woohoo! Yes. Yes, Miss Moore. It is elastic. Okay. All right. Moving on.
Here's a different situation.
0.067 kilogram ball bearing going 2 meters per second collides with an identical ball that's at rest. Okay. Oh, they both roll off together at the same speed. How fast are they going?
When we were playing, well, can we go back to this original pyramid here?
Let's do that.
What do we have to change?
Okay, well, we know that this is the same because it's the law of conservation of
Right.
momentum. And the second ball is not moving still,
So
right?
that stay the same,
So-
but afterwards we have their combined masses.
Okay, so they're no longer doing their own thing. This one at rest, this one moving. Now they're combined.
They roll off together.
So can we just call it momentum final?
Well, you could do P1 plus 2 final.
P1 plus 2. Oh, yeah. P1 plus 2.
Final.
Okay. Oh, final.
There you
I'm
go.
always forgetting. Don't forget your things.
Okay.
Okay, so now, oh, I can just skip the step. Oh, no, this is fine.
Yeah.
P1, 1 plus 2, like that. Okay, just bring this down here. So now,
Thing on the left is going to be the same.
this is going to be the same.
Although you can't cancel the velocities, but
Let me go ahead and rewrite this. M1, M2. So mass 1 times velocity 1 is going to equal, okay, so now it's going to be the mass of 1 plus 2,
yep, 1 plus a mass of 2.
okay, times the velocity prime,
Yeah.
okay, of 1 plus 2.
Yeah.
Okay, so we're trying to figure out the velocity still.
How fast? Yeah. So how do we get that by itself?
Well, now we have to divide by this, right?
Yeah.
1 plus 2, these cancel.
Yeah.
Okay, can we just plug this in here?
Let's do it.
Okay, so my mass 1 is 0.067 kilograms, and my velocity was 2 meters per second.
Yeah.
And then 0.067 times 2.
Yeah. You can either multiply or make them twice.
I'm gonna plug that in right now. 0.067 times 2. It's 0.134.
Yeah.
I should have known. 0.134 kilograms, and that's just the first ball plus the second ball. They have the same mass.
Yeah.
Okay, now let's go ahead and solve for this. Okay, so we've got 0.067, and I'm gonna put, oh, it actually doesn't matter. The top doesn't need to be in
No,
parentheses.
parentheses are good on this one.
Times 2 divided by 0.134. And here we go. And I get 1.
1 meter per second.
1 meter per second. So how fast are they going? 1 meters per second.
And that kind of makes sense, doesn't it? They both have the same mass.
Yeah.
So the
So they have to split that up evenly, right?
yeah, you got twice as much mass, you'll have half as much velocity.
Okay. Is this an elastic collision?
Well, we got the kinetic energy before already. It's
Yeah, the kinetic energy before
0.134.
was 0.134 joules. Now let's talk about after. So K equals 1/2 mv squared. So we're gonna do that combined mass, which is
0.134 kilograms.
4 kilograms, times our velocity, which is
1 meter per. I think you can square that one very
oh,
easily.
yeah, that'll be one, right? So we're just gonna do half of 0.134, which is, it should just be 0.067, right?
Well, yeah.
0.5 times 0.134 times 1 squared, and we get 0.067.
0.067, just as you predicted. So now the question, is this an elastic collision?
Well, before we had this, after we had something different, so the answer is,
No,
nope, it's not.
that is not an elastic collision.
Okay.
That's an inelastic
It is
collision.
inelastic. Okay. It is only elastic if the kinetic energy is the same before and after. Inelastic collision. Some kinetic energy is changed into heat, sound, etc.
Yeah,
So that's what happened here.
probably made a big bang when they hit.
Okay. A 0.067 kilogram ball bearing going 2 meters per second collides with an identical ball at rest. Okay, the first ball goes backwards at 0.5 meters per second. Backward at that, okay?
So that'd be
How fast
negative,
does the
I'll
second
bet.
ball- Yes. How fast does the second ball go?
Okay, let's go back over to what we've got before. What's going to be the
Okay.
same? What do we have to change?
Right. Get rid of this guy right here. Okay, so this line is gonna be the same. This side is gonna be different right here,
Right.
though.
Yeah.
Okay, so now we still have P1 plus P2, right?
Yep. And they're afterwards.
Oh, it's really important. And you guys like, there's more. It's not that it's important. Okay, so let's go ahead and change down here. Dang, is that the bell already? Okay, so mass one.
Well,
velocity
hang on. What are
one.
we going to solve for, though? Where,
Oh,
where,
you're right.
where does our answer live?
How fast does the second ball go? It lives over here.
So how do we get that by itself?
Oh, do you want to subtract the P over there real
Yeah.
quick? That's a good idea. Okay, so
You want to get to the complicated stuff as late as possible.
so we want to figure out the velocity it is of the second ball. So let's move this over here first.
Yep.
Minus P1 prime minus P1 prime. Okay, so now I've got P1 minus P1 prime, and you can see why the prime is important
Yeah.
now, equals P2 prime.
Yep.
Okay, and now we can put in our M and our V's, yeah?
Yep.
Okay, so M1 V1 minus M1 V1 prime equals M2 V2 prime.
That's right.
So let's go ahead and divide by this mass, yes?
Yep.
M2. M2. Okay, I think we can plug it in here. So the balls are both 0.067 kilograms, right?
They are.
Okay, so 0.067 kilograms times the velocity of the first ball, which is 2 meters per second, and this is the positive direction.
Yeah.
Okay, minus, and again, they're both 0.067 kilograms times, but our second ball, prime, our second ball prime goes backward.
At 0.5.
Okay, and that negative is super important. Okay.
Uh-huh.
How fast does the second ball go? Sorry, M2, M2, yeah, 0.067
Yep.
kilograms, boom, and that's gonna give us our second velocity. And you know what, all you need is this, right? is what we need.
Well, actually, you're going to have to keep those parentheses up there.
Yeah?
Yeah. Because you're multiplying in between, and then you're going to need brackets.
Yeah, I'll put the brackets around like this. We'll do 2 parentheses.
Like that.
Like that. Boom, boom, boom.
Boom,
Whenever
boom.
you got any additional multiplication, addition or subtraction up there, you gotta make sure everything's in there. Okay, so 0.067. I said bracket.
Yeah.
0.067 times 2, close parenthesis, plus 0.067.
That should be minus.
Oh, you're totally right. And there should also be minus. Gonna insert, because Miss Moore makes mistakes.
We all do.
Parenthesis minus parenthesis 0.067 times a negative 0.5.
Yep. Double.
Okay,
parentheses.
double, divide by 0.067, and
Yeah.
we get 2.5. That number makes sense.
Yep.
Okay, 2.5 meters per second. Okay,
Sweet.
So how fast that ball moving? 0.0, and check this out. If it's moving backward at 0.5,
Yeah.
forward at 2.5, velocity conserved. Okay.
Yep.
All right. So, were we gonna ask about
Nah.
No. Okay. Okay.
I'll tell you right now, it's an inelastic
Yeah.
collision.
Okay. So, how does our challenge? If you wanted to figure that out, do it now. How does our textbook's author justify the law of conservation of momentum? So, this is your big picture homework question.
Yeah.
In order to answer this question, I'd like you to go to page 207 to 208 in chapter 9.
207.
And you are going to read 2 particle collisions. That's right here. And as you read, or after you've read, I want you to identify and record the main idea of each paragraph and what sequence of reasoning leads to the law.
Okay, so we start on just this part has 1, 2, 3, 4 paragraphs. 5 paragraphs, and there's the law at the end. So how do they get to that?
So they should have 5 main ideas then, right? Is that what we want?
Yeah.
Okay. All right. Good luck. Go ahead and begin.
Bye.